All right, so now we're going to continue talking about this infinite dimensional manifold of probability distributions, and in particular we're going to talk about the associated KL divergence. So the KL divergence, right, is given by the following. So dKL, so between two probability distributions P and Q, it's integral of P of x log P of x divided by Q of x dx, which is the Bregman divergence, as you probably know by now, of the associated with that convex function, right, which is the Bregman divergence. And it gives you this dually flat structure. And F a dually flat structure. Then the Pythagorean theorem, right, the generalized Pythagorean theorem is as follows. dKL, it's like from P to R, right, is equal to dKL from P to Q plus dKL from Q to R, right, when the mixture, the M geodesic connecting P and Q is orthogonal to the exponential geodesic, the E geodesic, connecting Q and R. Which is to say that the integral from P of x minus Q of x dotted into the log of R of x minus log of Q of x dx equals to 0. And if we recall, it's like in the previous lecture we had computed the tangent vectors to the to the E geodesics and the M geodesics, right? And that's basically what we're using here in order to characterize the orthogonality condition, which we had talked about here. Okay. And then there's a projection theorem which follows on this. So you can expand, it's like the KL-divergence if you like. So let me just erase most of it, but leave the expression for the KL-divergence. So let's say that you're looking at this, but you want to look at P and Q nearby, right? So you can expand that expression if you like. So the KL-divergence between sort of two nearby distributions. Let's say p of x and p of x plus delta p of x, right, is expanded as so dkl p of x to p of x plus delta p of x is equal to the integral of p of x log 1 minus delta p of x divided by p of x dx. And of course, the reason why it's written this way is because if you recall, there's a Taylor expansion that's like for the log of 1 minus x, right? So we're going to use that. So this is approximately equal to 1/2 the integral of delta p of x squared divided by p of x dx. Right, that just comes from the fact that log of 1 minus x expands the leading order term is just x squared, right? And x here is delta p over p, so you get delta p over p squared multiplied by p, which gives you this expression here. Right, so with that, this is essentially telling you something about the Riemannian geodesic, sorry, the Riemannian metric, it's like which this KL-divergence is inducing on this problem. So the square distance of an infinitesimal deviation delta p, right, is dx squared is equal to integral of delta p of x squared divided by p of x dx, which is the Riemannian metric given by the Fisher information, right? So the bottom line is that most of the things, you know, it's like which we studied, it's like in the context of the discrete probability distribution extends in a fairly natural way. It's like naively, it's like to this infinite dimensional manifold of probability distributions, right? So you might think everything is hunky-dory, but one has to be careful, as I said before. And let me sort of show you where things can go wrong, okay? All right. So the question is, what can go wrong in infinite dimensions, right? Okay. All right. So one example is that we can define a quasi-epsilon neighborhood of P of x using the KL divergence. Sort of in the obvious way, right? So we want to have the neighborhood of radius epsilon in some sense. It's a set of Q of x with the property that the KL-divergence from P, which is the sort of the center, if you will, it's like of the neighborhood, to points Q, it's like in the neighborhood, that's less than epsilon. Right, so that's a eminently reasonable definition. It's like it's sort of the natural thing you would do if you're using the divergence function as if it was a pseudo distance. This is how you would define a quasi-epsilon neighborhood. Very natural so far. So the problem is that the set of quasi-epsilon neighborhoods do not satisfy the axiom of for a topological subbase. So the point is that you can't actually use this to define a topology on this space. So examples of other things which can go wrong are the following. Okay, so it can also be shown that the entropy functional psi of p of x, which is the integral of p of x log p of x, right? It's this negative entropy, is not continuous in F. But it is continuous and differentiable in Sn. Okay. So anyway, so those are just two of possible examples, or many examples, for why it is that one actually has to be careful to make sure that the kind of intuition it's like which we've developed from the finite dimensional case actually extends in a natural way. It's like, and it's well defined and makes sort of rigorous mathematical sense in the infinite dimensional case where you're dealing with probably distributions for continuous random variables. So that's just a word of caution, if you will. It's like, but anyway, it's certainly very, very natural to, you know, it's like at least attempt to proceed by trying to leverage the intuition we've developed in the finite dimensional case, and then seeing how far it's like we can push that analogy forward. Okay, so I'll just stop here for now.